A coaxial cable. A small solid conductor with radius A is supported by insulating non-magnetic disks on the axis of a thin-walled tube with inner radius B. So you can see this is the tube and we have the solid conductor with radius A. The inner and outer conductors carry equal currents I in opposite directions. So the current flows here in this direction and then the current flows in the inner conductor in the opposite direction. Part A, use Ampere's law to find the magnetic field at any point in the volume between the two conductors. So we take an Amperian loop with radius r from the center and we write the closed path integral for part A. The closed path integral magnetic field dot product with the line element on the circular path, and because the magnetic field will be only a function of r and it will be basically a constant throughout this path, this integral gives us b times 2 pi r, which is, according to Ampere's law, equal to mu 0 times the current enclosed by this Amperian loop. And therefore we find the magnetic field magnitude between R between A and B in the volume between the two conductors to be mu 0 I divided by 2 pi R. That's the answer to part A of the question. Okay, let's look at part B. Write the expression for the flux d phi b through a narrow strip of length L parallel to the axis of width dr at a distance r from the axis of the cable and lying in a plane containing the axis. Okay, so here is a strip of width dr at a radial distance r from the center, and the strip has length L as suggested. Now we want to find the flux through this strip. Because the magnetic field is constant in this radial distance range dr, we can say the magnetic field is B evaluated at r multiplied by the area, because the magnetic field is going to be tangential to this circle. It's going to be perpendicular to the strip. We can write d phi b is equal to magnetic field at r multiplied by the area of the strip dA. Now what is the area of the strip? It has length L, width dr, so it is L dr. Therefore we can find the magnetic field through such a strip to be mu 0 I over 2 pi r, the magnitude of the magnetic field, multiplied by the area L dr. This is the dot product, but because the magnetic field and area vector are going to be parallel to each other for the strip, the flux will be simply the product of the magnitudes, mu 0 I over 2 pi r times L dr. Okay, let's move on to part C. Integrate your expression from part B over the volume between the two conductors to find the total flux produced by a current I in the central conductor. Okay, what is the total flux? The total flux phi sub b is the integral from r is equal to a to r is equal to b. So we're considering all such strips in the volume between the two conductors, d phi b. So that is mu 0 I L divided by 2 pi integral, the constants are out of the integral, from A to B, dr divided by R. So here is our dr divided by R. That is what we're integrating over. And from A to B, this is going to give us natural logarithm B over A. So this is mu 0 IL divided by 2 pi natural logarithm of B over A. And we can rewrite this result here so that we can basically take it into a box. The total flux is mu 0 IL over 2 pi natural logarithm B over A. This is the answer to part C. Let's move on to part D. Show that the inductance of a length L of the cable is mu 0 L over 2 pi natural logarithm B over A. So in part D, we recall that the total magnetic flux phi is related to the current as inductance times the current. And this is basically the equation that defines inductance. So inductance is phi B, magnetic flux, divided by the current. And we already know what the magnetic flux is. Therefore, the inductance is mu 0 L over 2 pi natural logarithm B over A. And just to make sure we recall the analogy with capacitance, in the case of capacitance, the charge stored on a capacitor is the potential multiplied by capacitance. This is analogous to the magnetic flux is equal to the current times the inductance. So we can recall this analogy between the capacitance and inductance. Okay, so this will make it easier to remember. Part E, calculate the energy stored in the magnetic field for a length L of the cable. What is the energy stored? The energy stored is 1 over 2 Li squared, which is 1 over 2 the inductance mu 0 L divided by 2 pi natural logarithm B over A multiplied with I squared. So we can rewrite this answer. The energy stored is mu 0 L I squared over 4 pi natural logarithm B over A. And this equation is also analogous to the capacitance case. In the case of capacitance, the energy stored is Q squared over 2C or 1 over 2 CV squared. So just to remind ourselves, this is the case of capacitance analogous to the inductance where the energy is 1 over 2 Li squared. So here we have 1 over 2 CV squared. For the case of inductance, we have current. Capacitance, we have voltage. So here the voltage has become current, capacitance becomes inductance, and Q is analogous to magnetic flux. Okay, so in this problem we have a conductor that is insulated inside, it's on the axis of a thin walled tube with inner radius b, and it's insulated from the outer conductor. These two conductors carry currents in opposite directions, but because the current through this Amperian loop is only this current I, so this one doesn't make any difference. Only outside, if we take another Amperian loop, the two currents would give us a net enclosed current to be equal to 0. Okay, so first we use Ampere's law to find the magnetic field between the two conductors. And because the magnetic field will be circulating around this conductor using the right-hand rule, actually the thumb points in the direction of the current, the forefingers of the right hand curl in this direction, the clockwise sense, looking from this direction. Closed path integral B dot dl is B times 2 pi r, because magnetic field is only a function of r, and it's a constant along this path, and it's parallel to the length element, dl. So B times 2 pi r is mu 0 I, the total current that passes through this loop. So magnetic field magnitude is mu 0 I over 2 pi r. Now if we take a strip of width dr and length l, the length of the conductor, at this radial distance r, the magnetic field is constant. The area vector L dr in the direction, in the tangential direction, is parallel to the magnetic field. So the dot product is simply the product of the magnitude. So mu 0 I over 2 pi r L dr is the flux through this strip. If I consider all such strips going from r equals a to r equals b, I can calculate the total flux. The total flux will be integral a to b d phi b, and that gives me mu 0 I L over 2 pi natural logarithm b over a. Since the flux is inductance times the current, the inductance is simply the flux divided by the current here, and the energy stored is 1 over 2 Li squared, analogous to 1 over 2 Cv squared in the case of capacitance, and that's basically the energy density we will find.